So part four of the course, it's described as thermodynamic properties of pure substances. And what we're going to look at is what a pure substance is, and then introduce property diagrams and property tables that help us define the properties of a pure substance. So let's start by defining what a pure substance is. A pure substance is a substance that has a fixed chemical composition in all phases. You can have a mixture of various elements or compounds, as long as the mixture is homogeneous. So if you take a sample of it at any point, it's always going to have that consistency to it. And it can, if you take a portion of it in any phase, it'll also have the same consistency to it. So an example there would be water. It's got the constituents of H2O, but has the same chemical composition, whether it's in the solid, liquid, or vapor and gas phase. Other examples here are oxygen, nitrogen, helium, hydrogen, and so on. Dry air, although it's a mixture of these elements here, it's fairly consistent, so it's regarded as a pure substance. The only condition there is that if there's a degree of moisture in it, then its composition may vary. So that's why it has to be pure dry air when dealing with it from a thermodynamic point of view. And it's an extreme example, I suppose, of a substance that's not a pure substance would be a mixture of oil and water, because the oil and water will always want to separate and the oil will rise to the top. So oil is not soluble in water. Now, the reason why we're interested in pure substances in thermodynamics is because they make up the working fluids in a thermodynamic system. And the simple example there would be in the power plant. We describe the power plant as a heat engine, and the thermodynamic working fluid in a heat engine is pure water. And the reason why water is used is, first of all, it's readily available. It's also got good thermodynamic properties. It also is non-reactive and non-toxic, so it's not going to explode on us. And it's abundant. But beyond that, the reason why we have pure substances in thermodynamic as thermodynamic working fluids, some of these points may seem obvious, but it's because of their consistency and predictability. Pure substances have well-defined physical and chemical properties, allowing for accurate modeling and analysis. So if you don't have that consistency, then you can't be sure of your modeling and your analysis of, obviously. Phase equilibrium, the behavior of pure substances during phase transition, boiling and condensing, is well understood and characterized. So if we had a degree of salt, for example, in water, it would change its boiling point. So that's why it needs to be fixed every time. So pure water is free from any other contaminants, and we know when it's going to boil and when it's going to condense. It simplifies calculations. So once again, if we're dealing with something that has the degree of unpredictability to it, then the calculations are not going to work out, or they become a lot more complicated. And then also a pure substance can be used for those reasons as a reference point, and the examples would be the boiling and the freezing point of water and the triple point of water, which we'll cover in a few moments. When we use a pure substance as a working fluid in a thermodynamic system, it goes through phase changes. So it's important that we have a basic understanding of phase changes in thermodynamic systems, so on a molecular level. So phase change or phase transition is a process in which substance changes from one substance to one state of matter, solid, liquid, or gas, to another. This transformation occurs due to changes in temperature or pressure, resulting in the absorption or release of energy. So let's say we have a solid. It's got this 3D lattice formation where the atoms are equally spaced, but they still rotate and vibrate around those fixed positions. If we increase the temperature or decrease the pressure, we can turn it into a liquid. So the movement of the atoms in liquid form is a lot more fluidic, and they do still have a relative fixed position or relative fixed distance from each other. Then we go from a liquid to a gas, once again increasing temperature or decreasing pressure, and then the relative positions and the activity of the gas is much more chaotic. Over here we see when we go from liquid to gas, it's called evaporation and condensation. And when we go from solid to liquid, melting and freezing, as we know. But we may not be too familiar with the phase change from solid to gas is called sublimation, and in the other direction, it's called deposition. So why are we interested in phase change of a working fluid in a thermodynamic system? And the reason why is because it makes the thermodynamic systems do what they're supposed to do. Simple examples there would be the heat engine again, which drives the power plant. We boil up water and it's superheated or high temperature steam. So that's one phase change. That drives the turbine. And then we need to condense the low temperature steam back to water again. So there's another phase change there in order to feed it back to the boiler. In the refrigeration system, we have the evaporation of the refrigerant, which is the working fluid, which absorbs energy from the inside of the fridge. And then we have the condensing of the refrigerant back to liquid again to release that energy to the outside of the fridge. And that's brought about by the pressure difference from one side of the system to the other. So those phase changes are what's necessary for the refrigeration system to work as well. Now, engineers like to visually see what's going on in systems. And one way they can visualize a process, for example, is using property diagrams. So it says here property diagrams are graphical representations used in thermodynamics to illustrate the relationship between different thermodynamic properties of a system. These diagrams help in visualizing and understanding the behaviors of substances under various conditions. So the one thing they do is help us visualize the process. So here we see a PV diagram. When we go from one state to another, this could be an expansion, for example, of a piston cylinder device. We can visually see it. Now, those process paths can take different shapes. They can be straight lines, they can be curved, they can be curved at bigger degrees, or they can, have different configurations to them. And what it tells us is the nature of that process. Is it isobaric? Is it isochoric? Is it isothermal? And so on. And what we can also do is we get the area under that curve between those two states. We can evaluate the work that's being done during that process. We can do something similar with what's called a TS diagram, which plots temperature against entropy. And from that, we can see the amount of heat given or received by during a process. It can help us analyze cycles. So a cycle is a series of processes that begin at a point and end and terminate at that state, bring the system back to that original state again. And if we were to get the area under each curve in a cycle and add or subtract them accordingly, we will get this net value in the middle, which is ultimately the net amount of work that's being produced by the cycle. An example would be the compression, ignition, expansion, and exhaust cycle of the petrol engine. So it's the expansion, the power stroke that does the work first, but a certain amount of that work is put back in by the crankshaft to compress during the next cycle. So we find out what the net value is. That's the useful work that's being produced by the system. So analyzing the cycles is very important. Phase change analysis used to study phase changes such as boiling and condensing by showing conditions under which solid, liquid, and vapor changes occur. So this is a PT diagram, and it's also referred to as a triple phase diagram. It shows solid, liquid, vapor phases for a particular substance. So we can see at what pressures and temperature combination we're in the solid, liquid, or vapor phase, and when we're likely to to transition to one or the other phases as well. The last one here is defining state properties. So they can help determine unknown properties of a substance when certain property values are known. So on the PV diagram up here, if we know a particular state, we know the pressure and the specific volume at that point. Well, we can use an equation like this, one of the ideal gas equations, and from that we can calculate the temperature. Well, what I'm going to do now is going to go through some of those property diagrams and show what they're used for and how they're put together. But before I do that, I need to go through some standard subscripts that you'll come across and will need to know. So the subscript F here, you can see it shown with the specific volume. That's referring to the saturated state property of saturated liquid state of a property. So that's this point on a curve. It's the point at which the liquid is starting to turn into vapor. It's where it's starting to boil. And the VF will tell us on this particular diagram that this is the specific volume at that point. The G refers to the dry saturated vapor state of a property. So the subscript down here, and it's telling us, it refers to this point here on a graph, and it's telling us the point at which the working fluid is becoming fully vapor. So here it's got this, we have the specific volume at that point. And the FG referring to the property difference between the liquid and vapor states. So we take one value away from the other, and we get the difference, which is the change in specific volume between those 2 points. The S or SAT refers to the saturation point for temperature or pressure. So at 100 degrees and atmospheric pressure, water wants to boil. So we would denote that with an S or SAT, that's the temperature and the pressure at which it boils. If we raise that pressure, we also raise the saturation temperature, and we can denote that as well. And the critical point will come across as we go through the graph and the way the graphs are put together, but it's denoted by a subscript C or subscript CR. So this is what we call a 3D surface diagram. And it says here, in thermodynamics and material science, 3D surface diagrams can represent how a substance property changes with temperature, pressure, and volume or other variables. The PVT surface diagram is the three-dimensional surface that represents a relationship between pressure, specific volume, and temperature of a substance at equilibrium. So we know PV and T, it identifies a particular point in here. And we know then, are we in the solid? Are we in the solid liquid phase? Are we in the liquid vapor or above the critical point? And so on. Now from this, it's a complicated diagram. So we can pull these diagrams from it, the TV, PV, and PT diagram. And that's what I'm going to do now and show how they're constructed. But later on in chapter 4, towards the end, when we've covered enough content, I'll introduce these other diagrams here. Okay, so these are 2D diagrams. In 2D diagrams in thermodynamics and material science are simpler graphical representations that illustrate relationships between two variables at a time. So the TV diagram is looking up from the bottom, and it plots temperature against specific volume. The PV diagram is looking in from the front, and it plots pressure against specific volume. And the PT diagram is looking in from the side, let's say, coming in this way, and plots pressure against temperature. So let's look at TV diagram first. Again, it's coming in from the bottom here. So if you can imagine us with a piston cylinder device like this, and the pressure acting down on the fluid, which is water, is atmospheric pressure, and that includes the weight of the piston. and we keep the pressure constant. So this is what we call an isobaric process at constant pressure. So we heat it up 20 degrees. That's this point on the TV diagram. And as we heat it up, we reach what's called the saturated liquid point here, again denoted by the subscript F. This is the point at atmospheric pressure here and 100 degrees that the water wants to boil. And then what happens is the pressure and the temperature remain constant through this phase, the latent heat of evaporation, where all the energy goes into turning the liquid into a vapor. And then eventually we reach this point here, which is called a saturated vapor point. And it's where we're on the verge of it fully becoming vapor. As we increase continue to add heat to it, the temperature now starts to increase, and we go into the superheated vapor region. That's vapor at a high temperature. So this is the isobaric line, a line of constant pressure. This is our saturated liquid point, saturated vapor point. This is a transition here as we go from liquid to fully vapor. And during this stage here, both the pressure and temperature remain constant. Now, if we were to do that for a range of pressures, you can see these pressures here. You've got the pressure of 0.01 megapascals, 0.1, and then 8 megapascals and so on. And if we were to repeat this process for a range of pressures, these pressures here, we would get a series of saturated liquid points. And if we join them up, we get the saturated liquid line. Over here, we will have a range of saturated vapor points. If we link them up, we get the saturated vapor line. And where they coincide is called the critical point. Above the critical point, there's no distinction between the liquid and vapor phase. And the liquid, we're dealing with water in this case, and it takes on a new properties of what we call supercritical fluids, which have special applications. So we've produced this dome-shaped curve here. Over here is what we call compressed or supercooled liquid, which is basically just liquid water. And then we have superheated vapor region over here, which is just basically vapor at increased temperatures and pressures. And we have the saturated liquid vapor region. So this is a transition from liquid to vapor. And then above here, the critical point where we have supercritical fluids. Few points to make about increasing the pressure here. It says higher saturation pressures, water starts to boil at higher temperatures. There's a definite relationship between saturated pressure and saturated temperature, producing the liquid vapor saturation curve. So as we increase the pressure, so these pressure lines here, we see that the temperature at which we reach the saturated liquid point increases. So there's a definite relationship between the saturation pressure and the saturated temperature for a liquid. And for water, this is the liquid vapor saturation curve here. Below this point, we're in the vapor zone, and above it, we're in the liquid zone. The other thing to note is that as the pressures increase, the specific volume increases at the point at which it wants to turn into a vapor. That's because the pressures are compressing the liquid and stopping it forming and turning into a vapor. But then the higher pressure, the higher temperatures overcome that, and it starts to turn into a vapor. So that's the way these points move slightly to the side. In this case, to increasing specific volume. You also notice that the difference between the saturated liquid and the saturated vapor point starts to decrease with higher pressures as well. So it takes less energy to turn a liquid into vapor at higher pressures. And at some point, Vg equals Vf. The saturated liquid point and the saturated vapor point coincide, above which there's no clear distinction between a liquid and a vapor. It takes on a new properties of a fluid called a supercritical fluid. So now we're going to look at the PV diagram. PV diagram is coming in from the front here, and we produce a similar dome shape curve with the same kind of regions on it. So how do we produce this? Well, let's say this time we heat up the water, but we keep it at constant temperature. So this is what we call an isothermal process, a process at constant temperature. But we have a series of weights acting down on the piston. And what we do is we start to remove them. So this is point 1 up here. And as we start to remove the weights, the pressure starts to drop. At some stage, we will reach the pressure and the temperature, the saturated pressure and temperature, and reach the saturated liquid line. We don't remove any more weights, and the temperature we have as constant anyway. So pressure and temperature remain constant. All the energy is going into turning the liquid into a vapor. So ultimately, we reach the saturated vapor point over here. And then as we remove more weights, we enter the superheated vapor region. And this is a line of constant temperature, an isothermal line. If we were to repeat the process for different temperatures, we get a range of lines like this. And if we join up all the saturated liquid points, we get the saturated liquid line. And if we join up all the saturated vapor points, we get the saturated vapor line. And where they coincide is the critical point. Once again, over here, we've got the compressed or subcooled region, which is basically liquid water. And over here is superheated steam, a mixture of liquid to vapor in here. And above this point, the supercritical fluid. When we're dealing with water, the terms vapor and steam are interchangeable. So you might hear the term steam being used, and so we're specifically dealing with water in that case. You might hear the term gas being used. So gas is generally, if vapor is generally and steam is generally along here, close to the saturated vapor line. But as we increase pressures and temperatures, it's generally referred to a gas in this region. We can expand the PV diagram to include the solid phase, although in thermodynamic systems, we're not really concerned with the solid phases. But what we see by expanding the PV diagram to the solid phase is a line called the triple line. And the triple line occurs at a particular pressure and a particular temperature, but over a range of specific volumes. And it's the pressure and temperature at which the three phases of solid, liquid, and vapor can coexist. So it's often used as a reference point in thermodynamics. And at one stage was used as a reference point to help define the Kelvin. There's a distinction between pressure, the PV diagram for most substances and for water. So water expands upon freezing, which is not many substances do that, and the reason why it does that is because of its unique crystalline structure when it's in the phase of the solid phase as ice. And because of that, then this line here is got a negative slope for water, but for other fluids, for other substances, it looks more like this. So this is the third graph that we can pull from our 3D surface diagram, and it's called a PT diagram. So it's looking in from the side here. And this is also referred to as the triple phase diagram because it shows the three phases: solid, vapor, and liquid for a substance. The zero reference down here on a triple phase diagram is for pressure is perfect vacuum, absolute zero, and 0 Kelvin for temperature. So absolute zero for temperature as well. But we can see the sublimation line. This is the line, we cross this line and we can go from solid to vapor or vice versa. We've got the melting line where we can go from liquid to solid and vice versa, and the vaporization line where we can go from liquid to vapor and vice versa. And just the distinction again for substances that expand on freezing, such as water, that this melting line is over here, like this, but substances that contract on freezing are more represented like this. And the triple line that we've seen and introduced on the previous slide is represented as a point on this diagram. So here's the triple line here, but when we're looking in from the side, it looks like a point because the triple line occurs at a particular pressure and a particular temperature, but over a range of specific volumes. And this is the PT diagram once again. And if we were to draw a line of constant pressure at atmospheric pressure, we would see that this would be the freezing point for water. This would be the boiling point for water, but this would be the freezing point for other substances. The critical point we've introduced, it occurs at 647 Kelvin on a pressure of 22.1 megapascals. And above that point, the fluid takes on supercritical properties, the properties of a supercritical fluid. So in thermodynamics, a critical point is a specific combination of temperature and pressure at which the liquid and gas phases of a substance become indistinguishable. At this point, the properties of the liquid and gas phases converge, resulting in a single homogeneous phase known as a supercritical fluid. So supercritical fluid is highly compressed fluid that combines the properties of gases and liquids. They're created by increasing temperature and pressure beyond the substance critical point. A supercritical fluid can diffuse to a solid like gas and dissolve materials like a liquid. This makes supercritical fluids useful in various industrial applications. So it's used for extraction, materials processing, drying, and chemical reactions. So a few examples: coffee beans. If you wanted to make decaffeinated coffee, you would extract the caffeine out of the coffee bean, but traditionally that would affect the taste of the bean and its structure and its integrity. But by using supercritical fluids, you can extract that caffeine, but preserve the taste and the integrity of the coffee bean. So there's no distinction taste-wise between decaffeinated coffee and normal coffee by extraction using supercritical fluids. Materials processing can be used in the production and processing of nanomaterials. They are particles that have dimensions less than 100 nanometers and have very, very special properties. So for example, if you were to cover a sheet of paper with pencil, and if the thickness of the coloring was about 1 atom thick and you were able to peel that off, what you'd have is an example of a sheet of material that's referred to as graphene and made of nanoparticles. And graphene has the strength, the tensile strength, 600 times stronger than steel. So they have amazing properties. There's a lot of challenges trying to produce them, but supercritical fluids can be used in the production and processing of nanomaterials. Drying. So if you want to dry and preserve food, for example, drying can destroy and change the structure of delicate foods. So things like herbs and delicate fruits, if you dry them using supercritical fluids, it preserves their structure and leaves them unaltered. The triple point in thermodynamics refers to the specific conditions of temperature and pressure at which three phases of a substance coexist in equilibrium. So we've shown that there. It's the triple line on two of the diagrams, but it's a point on the PT diagram. It was used as a reference to define the Kelvin, around 2019 there was a redefinition of the SI base units, and it was slightly redefined. But it can still be used for the calibration of very sensitive thermometers and other various scientific measurement systems. So the three phases, solid, liquid, and vapor, coexist at 273.16, which is 0.01 degrees Celsius, and at a pressure of 611.7 pascals.
Every substance has a critical temperature and a critical pressure. When a substance is subjected to temperature and pressure that both exceed these critical values, it enters what is called a supercritical state. Any pure substance can exist in three phases, can be a solid, a liquid, or gas. We can show these phases using a temperature-pressure diagram called the PT diagram. This graph shows the location of the different phases of a pure substance in relation to pressure and temperature, with pressure P on the vertical axis and the temperature T on the horizontal axis. The three phases are separated from each other by so-called separation lines. We have the sublimation line, which divides the solid and the vapor phase. The sublimation line ends at the triple point, which is the point where all three phases coexist. There is a melting line between the solid and the liquid phase, and the vaporization line between the liquid and the gaseous phase. The vaporization line ends in the critical point. The temperature on this point is called the critical temperature and usually gets designated the symbol TCR. The critical pressure has the symbol PCR. These values, together with the critical density, are characteristic for each substance. With pressure and temperature that exceed the critical values, the substance will become supercritical and the differences between the liquid and the gas phase disappear. Let's see how this works in practice. For this experiment, we made our own pressure tank. It has a thermometer, a pressure meter, and a pressure relief valve. We also have some dry ice, which is carbon dioxide in the solid phase, a heating plate, and a heating base. We put some dry ice into the tank and seal the tank. As the pressure tank is completely sealed, the pressure builds. The dry ice starts at a low temperature, but with the rising pressure, it soon turns into a saturated liquid vapor mixture at about 40 bar and 5 degrees Celsius. By applying heat to the tank, we increase the pressure and temperature towards the critical point at constant volume. CO2 has a critical temperature of 31.25 degrees Celsius and a critical absolute pressure of 73.9 bar. So we want to heat up the carbon dioxide to its critical temperature, and because the volume of the tank is constant, we can also build up the pressure. As the pressure and temperature reach the critical point, the distinction between the liquid and gaseous carbon dioxide becomes less visible and eventually disappears. the phase boundary between the liquid and the gas vanishes. The CO2 is now in a supercritical state. To return to a state below the critical point, we will cool the carbon dioxide and make it reappear in the saturated liquid vapor mixture. By removing the heating plate and then adding dry ice on the aluminum cylinder, we can observe that the liquid vapor interface suddenly reappears as the temperature decreases. We have returned to the saturated liquid vapor mixture. Supercritical CO2 is used in a variety of applications, for example, to remove caffeine from coffee beans.